This is an overview of kind of additive manufacturing, state of the art, what it is, and you know, a bunch of the different technologies that make it up. So you may have heard of 3D printing, you may have heard of additive manufacturing. Essentially, they're the same thing. It started out being known, actually one technology, specifically Z-Corp technology, was the one that minted the term 3D printing, because it was like taking 2D printing and using powder to make it 3D. And then the industry, you know, it was like known as that. It was known as rapid prototyping. And then the industry really made a conscientious move about 8 to 10 years ago to try to change the narrative. So people were thinking of it more as an end solution to manufacturing. So they changed the term to additive manufacturing, which is kind of the contrary to subtractive manufacturing, which is what you would think of when you were like milling material or something like that. So what is additive manufacturing? So you guys can all see my screen, right?
Yep.
All right. So you may think of additive as just like filament printing, like MakerBots or Ultimakers and that sort of thing. But this kind of like broad overview, what I'm trying to show here is that there's actually 7 major families that is recognized by ASTM standards that form the overall additive manufacturing ecosystem. And the other thing I want you to note here, and like obviously the text is too small to read any of this, except for hopefully the dates. So when you look at these dates, we think so much of additive as this like brand new technology. We just started it. But in fact, you know, the very earliest technology goes back to 1986. And the kind of like earliest of the 7 families was still pre-2000. So actually it has a long history. I go to the big additive conferences and we laugh because, you know, we've all been there for like 25 or 30 years. And you know, we have a long history with the technology. So it's not super new. It's been in development from a long time. I'll kind of explain why, like in 2000, it was kind of discovered by mainstream media, and that's what kind of gave the rise to consumers understanding it, and more lay people understanding the term 3D printing. But it has been around for a long time. But independent of those 7 families and the 7 different like major components that make up the ecosystem, the process is kind of the same across all of them. And it's generally like what I like to talk about as a 3-step process. So you start with a virtual model. You can get this through CAD, obviously, you know, and really it's any CAD program that creates a 3D model. We take that data, and you can just create it from scratch. You can take a scan. You can take a scan and modify it in CAD. You can take, in the case of medical applications, you can take MRI data, and you can generate a 3D model. Then the computer, there's a slicing software. We call it a slicing software because it actually slices the 3D model into thin little layers. And that's kind of the second process. So we take the virtual model, has to be digitized in a way that like any slicing software can do that. Right now, it's STL files, and it has been since the beginning. There's been a lot of effort to try to change that because STLs have some issues, but still that's still an accepted industry practice is STL files. And then the third part in the process is what the machine does, which is take those layers and reassemble them one by one. Now, the thickness of those layers depends on the technology you're using. So they can go all the way down to, you know, 5 microns, all the way up to like several inches, depending on the material and the technology we're using. But essentially, independent of those 7 different technologies, it's the same thing. We're just assembling these things layer by layer. So why do we talk about this? Why is it important for a class where we're talking about materials, where as engineers, we're thinking about how to make things? And there's a lot of advantages to additive. There's definitely some disadvantages as well. But I'm here to talk about why we like it. So I'm going to talk about mainly the advantages. So the first and foremost is it kind of gives you this concept of unlimited geometries. So if you think about machining, if you think about casting, those things, like if you have a machine, you have to get a tool bit in places in order to be able to, actually cut out or subtract material. If you're casting, you have to be able to get the part out of the mold. Those all create limitations. Because in additive, we build layer by layer, a lot of those limitations go away. And so we can start to really think about what we would consider kind of unlimited geometries. Because we have unlimited geometries, we can create lighter weight parts. That means we can put the material where we need it, and we can take away material where we don't. And that allows us, in the world of engineering, we call this topology optimization. So if you haven't heard that term before, that's one that I'll probably throw around a couple times during the presentation. But that's our ability to create lighter weight parts by removing material where the material isn't doing anything, and maybe thickening up spaces where there's more forces being applied to a particular part. Because we have unlimited geometries, because we're creating lighter weight parts, we use less material. If we think about its corollary, which is subtractive, we start with a big billet of material and we remove what we don't want. So all of that stuff we're removing is becoming chips or pieces, and that's waste material. With additive, we're only using really pretty much the material that we need to make the part, and so it's a little bit more economic as far as material usage. Number 4, it allows for mass customization. So if you think about making a mold, I make a mold, that's a really expensive part. That could be $500,000 if I'm making an injection mold. Well, that's great. And then I can pump out parts by the thousands. But the problem with that is, we're not all the same size. So if I'm making something that interacts with the human body, every human is different. And so that mold, maybe I make 3 molds, small, medium, and large. Well, none of those are going to fit any of us perfectly. But with additive, we can actually we don't have to make a mold, we just make the part. And so that allows us to, because there isn't any mold involved, the printer doesn't care whether it's making 1 of the same thing or 30 of the same things or 30 different things. It just thinks about it as layers. So it allows us to mass customize parts for individuals, for different applications, without getting into the overhead of creating molds. Number 5, it reduces time to market, which allows for this iterative design. I can produce parts, I can prototype, I can change things, I can come back, I can do it much more quickly than I could if I had to go to a traditional manufacturing method. In the world of manufacturing, it allows me to directly create tooling, jigs, and fixtures, which allows me to make things faster. And lastly, it requires less manpower to run additive. So I can have one person run 10, 15 different additive machines. Whereas if we're thinking about traditional manufacturing, again, you kind of have at least one person running each machine. So it's much lighter on the labor side, which makes, our, as a US company, that makes us a lot more competitive because our labor costs are higher than, say, in China. So that allows us to make parts cheaper. All right, so I said there's some downfalls to additive. And when we look at this slide, you can see kind of this main downfall, which is the need for support material. So the general rule of thumb in additive, and this is a really critical thing here, is that you have this 45-degree rule. So any angle that is steeper than 45 is self-supporting, because you break this thing up into little layers. Each successive layer sort of only steps over a little bit. Gravity doesn't play that much effect. But the minute you start to go over that 45 degree, you start to have gravity affecting this thing, and you're going to get material drooping. And so what we have to do is what we're seeing on the right-hand side of our slide here, bottom right, which is you have these little columns of support that stick up that end up supporting that, which is great. I mean, we can solve that problem by adding support material. The problem is that gets back into, well, I take this part out, now I have to remove all those supports before I can use it. In many cases, like with filament printers, oftentimes we're only using the same material for both the part and the support material. So the interface between those two kind of gets a little nasty. It's not super clean, then you have to sand it, and it's a lot of post-processing. Now, not all AM technologies have this limitation, and I'll try to talk about those as we go through the list. But it is a very real concern, and it's certainly going to be with your project that you're going to be doing for class, where you're making things with the filament printers, you have to take that into account. And so the top slide here, you can kind of see, if you have this little overhang on the far left, no big deal. But as that overhang extends and you're not adding any support, you start to get this little, spaghetti strands that hang out under the part. All right, design for additive, it's become its own engineering discipline now. And so there's actually a bunch of different universities that have majors around DFAM, or design for additive. But you can kind of see the idea or concept, hopefully, when you look at a couple of these pictures on the right. So this is topology optimization in the top top right here, where you have a traditional part, and then you have a part where you've applied topology optimization. You've gotten rid of all of the material that's not doing anything. Again, that lighter weight part idea. You see that same thing sort of happening in the bottom right. On the bottom left, this is an entire bike frame, titanium bike frame that's made in one single print volume. And then they just kind of snap together. It's titanium. It's an incredibly lightweight frame. And actually, this is made on the same metal printer that we have at Lehigh. It's a Renishaw AM400 that made that bike print. So I can print an entire bike frame in one single thing. But this is the other part of design for additive. You want to minimize the support material usage, right? And you want to maximize how you put parts on a bed. And so you have to understand kind of the limitations of how that's being used. In the world of DFAM, it's the very tip of the pyramid, if you will. Really, there's rapid prototyping that's been around for a long time. A lot of people are using 3D printing for that. There's reproduction parts. So you have something like a 1930 Jeep, you can't get parts for it anymore. Well, if we can scan it or create a file for that, we can 3D print a part and replace those parts. The parts consolidation idea is taking multiple different parts, like 17 different parts that normally be assembled together in an assembly process, and just print it as one thing. So those have all been kind of used. DFAM is kind of the tip of this iceberg and where kind of we're headed with additive. All right, so getting back to the technologies themselves, I'm going to kind of run through these so you get an understanding of what they are. I'm going to kind of go in pseudo-chronological order, although it's not entirely that way. We're going to start with the very first technology. This is called vat polymerization. This is developed way back in 1983 by Chuck Hull. He's like, if you go to the additive conferences, he still goes. He's in his 70s now, but he's like the hero in the room, right? He's like the celebrity in the room. He's considered the grandfather of additive. So he came up with this process. He was a scientist working in a lab, looking at UV inks for printing. And the story goes, he and a bunch of friends went out for lunch one day. They came back, none of them really felt like doing work. He was sitting at his lab bench. He had a petri dish of this UV curable ink and a UV laser shining down. And he was just messing around, and he wrote his name in the petri dish in cursive script, Chuck, across the petri dish. And he grabbed his tweezers and pulled it out. And he's like, oh, that's kind of cool. And then he stuck it down back in the resin and kind of pushed it a little bit lower, and then traced his name again with the laser and made it thicker. And he had this kind of epiphany moment. If I can do this with my name with this system, I can kind of do it with anything. And so he had the company he was working for. He went to them and said, hey, I have this other potential use. And they're like, you're crazy, Chuck. We don't want anything to do with that. He's like, do you mind if I explore it? And they're like, whatever you do in your own time is up to you. So he in classic entrepreneur form, he didn't quit the company. He kept working for a couple of years and started a little project in his garage where he built one of these machines. It was pretty rough, but essentially it proved the point. And he built a whole company called 3D Systems out of this. So the way this works is you have a UV laser that's kind of up here at the top that fires a beam that gets focused through a bunch of lenses. It hits a galvo mirror, and that galvo mirror allows that laser to kind of dance across the surface. Below this, you have a vat, that's hence the term we call vat polymerization. You have a vat of liquid resin. And that liquid resin is UV sensitive. So anywhere that UV light hits, it's going to cure. It causes a chemical reaction that causes that resin to cure. And so what you do is you start with the build platform all the way up at the top of the resin tank with a very thin coating of resin on top. The laser fires, and wherever it hits, it solidifies, and then you sort of move down and step this up layer by layer. Incredibly high resolution parts. Traditional SLAs, they're printing at 10, 15 micron layers. So to give you a sense of scale, you guys are civil engineers, so you probably don't know the micro scale side of things, but a human hair is about 110 microns. So 10 microns, we're printing at 1/5 the thickness of a human hair at a time. So you get incredibly high resolution, but the overall cost of these machines is expensive. One of the classic uses, Invisalign braces. So here's a great understanding of how we can take digital production and really make mass customization, right? That thing I talked about. So you take a mold of the teeth, you digitize it. A technician, slowly moves the teeth. They create 30 to 50 different iterations to get them closer and closer to perfect. And then what do? That it would be impossible to like make physical molds of each of those and then actually like create a plastic part that you could send to people. So what do? They take those digital files, they send them to a 3D printer. It creates the positive mold. They vacuum form over the top, and they cut out those vacuum form pieces and send those trays. So entirely digital process. There's no physical thing except for the mold being created by the additive technology. By the same token, usually I ask people, but because we're on Zoom, it makes it more difficult. Usually ask me, anybody know what this is? But the answer is they are hearing aids. So again, that idea of mass customization. So here on this tray, you're looking at like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 15 different hearing aids, all on these little support materials that are being held up. And this is, again, mass customization. So they take a mold of your inner ear, technician hollows that mold out digitally, so that they can fit the technology of the hearing aid into it, puts a hole in there so that like the sound can come in and out, and then they send them to the printer and print them, clean them up, and that's the thing that goes in your ear. And so again, mass customization, everybody's ear canal is different. It allows for a lot of different applications. We can use the same technology for early stage investment casting. So here we're using a technique where we're creating a honeycomb structure interior with a resin that burns out very, very easily. So you take this part, you dip it in a ceramic slurry. A couple times, you put that ceramic slurry in a kiln. And while the kiln is curing the ceramics, it's also burning out the resin inside, which leaves you with this ceramic shell that's totally hollow. And now I can take liquid molten metal, pour it in there, and do a casting, what we call an investment casting. And that gets us a metal part very, very quickly without like creating a mold, which would be very, very expensive. This is a much faster molding process. All of that, again, these big expensive machines have given rise, and you'll see this is kind of a common theme, to this kind of consumer grade version. And Formlabs came on the scene as soon as the original patents expired from Stratasys. And if you come over to the Powerhouse, we have 3 of these now. We have a 4th on the way. These things are like $3,000 to $5,000 instead of $500,000, so it's much more accessible. There's a whole suite of different materials we can use to make really complex parts. So SLA has been around since the beginning. One of the problems with it is it's incredibly slow. So I said it's really high resolution. We're doing this 10 micron layers, awesome. But if you think about that, we have to do a lot of layers to make up an inch of height. Right? So there, if you're making something that's like 6 inches tall, you might have 20,000 layers in there. Each of those layers is a pass. The resin has to be moved back across the surface. Each of those things may take 30 seconds, 40 seconds to happen. You multiply 40 seconds times 20,000, and all of a sudden you're talking about days to get a part out of a printer. And so carbon technology came on the scene. They looked at this, said, how can we improve this, make this faster? And so they came up with this clip technology, which essentially cribs off of SLA, but it's 25 to 100 times faster. So what this does is it has the same resin tank. It's a little upside down now. Instead of having a laser firing from the top, we now have a LED projector from the bottom, which is projecting UV light. And the build tray comes down to the top, gets mushed into the resin tank, and it's essentially playing it's creating a whole image of a tool path in one shot rather than moving the laser. So that expedites that part. But the other part that is problematic with this is moving the resin across the build tray. And they solved that with science. They created an oxygen permeable glass, which allows oxygen to permeate just the first like 0.5 millimeter of the build tray. The resin won't cure in the presence of oxygen. And so that first millimeter becomes a dead zone, and that allows the resin to continuously flow. And so they don't have to make the resin move at all. It just moves on its own, and they essentially just pull these things up out of the tank as it goes. So you can see here's a part being printed. You can see the open kind of lattice structure. Again, almost impossible to do that with anything else, or impossible to do that with any other technique aside from additive. But it's given rise. I'm going to try to play this movie.
We love football. The rivalries, the unbelievable plays, the storied tradition, the wins and the losses. Athletes giving everything for the team, leaving it all on the field. It's the players that make the game and the communities that make it whole. Protect them, and you protect it all. Introducing Riddell Diamond Technology powered by carbon. Diamond technology replaces the current helmet liner with a 3D printed lattice for advanced impact absorption. Riddell uses 3D scanning technology to ensure a precise custom fit for each individual athlete. Combining this with data from on-field impacts, the Carbon Lattice engine automatically designs and simulates over 1,000 options and selects the optimal liner for each athlete. This custom lattice liner further manages both linear and rotational impact energies. Using a highly damping elastomer, these lattice liners are 3D printed with Carbon's revolutionary digital light synthesis, grown from liquid, crafted by light and oxygen. Our partnership with Carbon and the introduction of Diamond.
So, like, this is revolutionary, right? And so Carbon was sitting on this technology. They were really looking for adopters of this technology. They want to do this digital manufacturing solution. And so they were looking for people like who has digital technology, digital files that we can replicate with 3D printers. And so as they were sort of searching for places, industries to make an impact, they came across Riddell. Riddell makes all of the helmets for NFL. And, you know, these NFL players are getting millions of dollars. They want the best protection, right? The whole concussions on the field has become a big thing in the last couple of years. And so Riddell has been 3D scanning athletes' heads for like 20 years because they make like custom molds for foam liners and they cast the foam specifically for each athlete's head. So Carbon said, hey, you have the digital files. We think we can do the casting part better. Can we team up on this? And so Carbon worked with them. They gave them the files of the athletes' heads. They came up with their engine, the whole software package that they put sensors on the players' heads to determine, hey, you're a defensive lineman, where and how do you get hit in your helmet? And then they take that data and figure out the best impact absorbing lattice for that particular player based on on-field data from their helmet. Then the computer generates that thing, they send it to the printer. That's the easy part. The printer just prints it, right? And they can print a whole pad set in under 30 minutes for a specific player's helmet. They just pop them out, clean them up, put them in the helmet, and it's good to go. And so this has actually been on the field in NFL. 3 years ago at the Super Bowl, that was the first time the Riddell helmets had been used for a game in the NFL. And then after the Super Bowl, every NFL team now uses this technology for their helmets. And so they're trying to think of they're trying to get it. There's going to be a generic version for like high school athletes as well. But then kind of as you move up the pros, you get this like specifically tuned thing for your head. Totally fascinating, but only possible because you can print that quickly. All right, we're going to shift gears here, moving away from this kind of resin-based curing to this idea of material extrusion. This is kind of the second oldest technology. It's developed by Scott Crump in 1988. And again, I love these stories, and hopefully this gives you all a little enthusiasm for ideation, I guess, because it's like, necessity is the mother of invention, right? So Scott, as the story goes, his daughter had a project due for school. It was like the night before. She needed a diorama, and she needed a frog in her diorama. And they looked around the house. We don't have any clay. How are we going to make a frog? And Scott's like, where's the hot glue gun? So he grabs the hot glue gun and he starts to like sculpt a frog using hot glue, right? And again, just like with Chuck Hull, he has this epiphany, like, oh my gosh, I can do this and create this frog out of a hot glue gun. If I put this on a computer, I could train the computer to create the same frog over and over and over again. And so, he took that idea, he replaced the hot glue gun with an extruder that heats up plastic and squirts it out, and bam, this thing that we understand of as 3D printing, all of those maker bots that we use, this is the technology that came from that epiphany. So again, he commercialized this under a company called Stratasys. And this is what I said earlier, that patent life is only 20 years. And so he commercialized it in 1990 or 1989, I guess, is when he filed the patent. 2009, that patent expired. And MakerBot was like right there. And they were like, hey, this is super simple. These machines cost $500,000. We can make one that costs $500. And so that's what they did. And that's when people like us who don't have $500,000 sitting around, but maybe can scrape together $500 or $1,000, started to be able to access 3D printing. And that's when I think modern mainstream media really said like, oh, here's a new technology where it's just making stuff out of nothing. And that's when people really started to discover additive, even though it had been happening for over 20 years. If we look at this technology, we have this build tray. This moves up and down. We have an extruder head, and we have our filament over here on the left, and those come in spools. The filament unrolls, it goes up into the extruder head. The extruder head heats that plastic up to the point where it's molten, squirts it out of a little nozzle. That nozzle moves around and it creates those tool paths, or those layers, each of those slices successively as it goes up. This is really susceptible to gravity, so you have to have a support material anytime you're breaking that 45-degree rule for the most part. And so you have some printers have a secondary material that can be dissolved or washed away. Sometimes that support material is just the same plastic with a single extruder. Most everything that we have at Lehigh, we just use that single extruder model because they are cheaper. But that's the process. Production scale machines, again, they're huge. They cost hundreds of thousands of dollars, but they make really nice parts. Industries, I mean, you name an industry, they have 2, 3, 4 of them in, I regularly talk to Lehigh engineers who've gone into industry and come back and been like, man, I didn't even know we got like 5 3D printers down the hall from my desk, right? They're just all over the place because people are using this as a tool to prototype, to make parts. It is plastic laid on top of one another. So the interstitial layer strength is not isotropic, it's anisotropic, which means you get really good layer properties in the XY orientation, but you don't get as good orientation in the XZ direction because the plastic's cooled a little bit before the next layer of plastic is put on. And so they haven't, the fusing is actually really good, but it's not 100%. So you start to see some negative layer, negative properties there. But again, if you look at this picture on the right, how else are you going to make that thing, right? It's a really cool way of making stuff. Again, I talked about this. That expiring patent gave rise to these consumer grade machines. I can't even tell you how many companies are making these. Over 200 companies are making these small things. The ones you've probably heard of, MakerBot, Ultimaker, Dremel, those are the ones that we have at Lehigh. But you can buy kits for $300 that you put together, it's all sorts of stuff. But this is it, the MakerBot, that's really the revolution that brought it, put it in consumers' hands. And I like to talk about this as, this is the beginning of the democratization of design. So previous to 3D printing, you had to have an enormous skill set in order to be able to make anything, right? You have to be a machinist, you have to be a master woodworker. Now, as long as you can learn how to use a software package, you can design and literally make almost anything. And that's true across the spectrum, right? Because we have this ability to print plastic in our houses now, or at Lehigh, we've got 40 some of these machines sitting around printing stuff. But if you need better properties, we can print in metal, we can print in all sorts of other stuff. So it's allowed kind of lay people, I guess, access to the ability to make custom designed things for themselves. So you want to make a new pair of headphones that are just unique to you, you can totally do that now, right? That's the excitement. Once we start to extrude material, the Pandora's box is open. Everybody starts to think about different ways of doing this. How can we make these stronger? How can we do these differently? There's composite extrusion where we're taking plastic and the plastic itself is limited in its structural ability. So we take plastic and we extrude a continuous carbon fiber or glass fiber encased in that plastic. Now we get incredibly strong parts. These are this is a company called Markforged. Here they have, these are motorcycle brake handles, and they have just a plastic one. They have a plastic one with glass fiber. The middle one here is plastic with glass fiber, and then they have plastic with carbon fiber, and then they have this kind of combination version. Every single one of these that has the continuous fiber is as strong, if not stronger, than their aluminum counterparts that you would originally find on the motorcycle, right? And so that's the ability. Now I can make a custom brake handle. I can, replace a brake handle. I can make it lighter. These are actually all lighter than the aluminum as well. So it starts to become really exciting. We can start to think about what else can we extrude, or what can we extrude sort of at the same time. So this Voxel 8 company is working on like doing digital circuitry. So they're printing, and then, the plastic print head takes a break for a second, and then it comes back with this like silver ink that's conductive, and it can actually print your wires internal to your geometry in the same component. And so they make, my favorite part about this is they have a hexacopter that they printed from the ground up. They paused it, they dropped in a motor, it connected the motor to the battery pack that they dropped in. They stop the printer, they take it off, pop on some propellers, and they fly this thing, right? Totally amazing to see how you can sort of apply this to other things. It's not just 3D printing, it's not just for small stuff. We're starting to also see the kind of like world of larger structures start to be printed with different technologies. One of the first on the scene thinking large scale is this BAM concept. It was built at Oak Ridge National Lab. Now there's a company, Cincinnati Industrial, that's making these things. These things are huge. The new ones now, the Cincinnati, the last time I talked to my friend there, they just did one that was 20 feet wide by 50 feet long, right? That's the scale of these printers. But this started at an 8 foot by 8 foot size. They had a big CNC router that was like doing foam that wasn't being used at Oak Ridge. So they took off the router head, they replaced it with a double screw extruder head that heats up plastic and squirts it out. And they started printing a 1/2 inch diameter bead of ABS carbon fiber plastic. And they started making these big parts. And so they just had this, for them, it was a kind of like a opportunity, right? Everybody's making like thinner and thinner, smaller nozzles to do higher detail. What if we don't care so much about detail? We just want larger structures. And so again, normally I would say, like, anybody know what this is? The answer is, this is the start of this, right? So this is Cincinnati Industrial's first machine. They printed out this car. This is at the IMTS show in 2014. They started the car on Thursday. The whole body of the car is printed. And this Saturday, they were driving it around the IMTS show. So kind of crazy how quickly you can make this stuff happen. Lonnie Love, who is the director of additive at Oak Ridge, said, "That's great, but man, I mean, this is kind of a cool car, but I hate all these lines, right? And you can actually see how this thing is printed, all of these steps of the polymer. What can we do to process this better?" And so they came in and they did some smoothing, and then they did some painting. This is not an actual Cobra. This is a 3D printed Cobra, right? And you can see the kind of like quality. They obviously sent it to a paint shop and painted it up really nice. But this is a plastic body that's been recreated from a 3D scan of an actual Cobra, printed with this technology very, very quickly, right? This is like a day's print. For something of this scale, and then probably a couple of days to clean it up and get it to that thing. All right, we do it with plastic. Well, we can also extrude with metal. And so if you ever have used a MIG welder, just think about this, right? It's a MIG welder. The welding wire is continuously being fed. You pull the trigger and you lay a weld bead, right? Well, if you lay a weld bead on top of a weld bead, now we're 3D printing. And so, there's a bunch of companies doing this. We built one. There's one of these in Wilbur that we built from scratch that we're using for some research. Lincoln Electric sponsored it. And we're able to do large scale parts like this. This thing is probably 2.5 feet tall. You can see it's just layers of weld beads, one on top of another. It's what I would consider near net shape. So it's not like perfectly smooth, but if you combine this with a CNC mill at the same time, you can mill each of those layers after they're laid down. And now we can get like a perfect, overall geometry. And this is actually like a turbine geometry. It twists as it goes up. Again, very complicated to try to mill from a single piece, but we can 3D print it very, very easily. In the world of this should get you all excited, right? All you civil engineers. So people start to think about applications of additive. This is one of my favorite examples. Amsterdam had a competition for a bridge design, a pedestrian bridge to go across one of the canals. And these two engineers hated kind of like all of these, like, you know, you can see the kind of like natural surrounding here, a lot of trees, a lot of grass. This is a rendering, so I want to be clear about that. This is a rendering, but this is their concept idea. They wanted a bridge that kind of melded with the environment, and they thought about, like, well, you know, we could do these like tree-like structures, these branch-like structures that could do the support. How do we actually make that? It's impossible to, like, you know, cast these things. How would we do this? And so they came up with this concept of this like robotic welder, which is just a 3D printer. And so the idea is you like lay your concrete foundations on the two banks of the river. You have 4 of these robots, 2 on either side. They start to print their own track that they ride on as they print the bridge, and they eventually kind of like join together in the middle, right? Voila, we can create like bridge scale structure out of metal with this incredible lattice structure that's lightweight, that's beautiful, that blends in with the environment. So they are still working on this. The last time I looked at this was probably a year ago. They had maybe not quite so as refined as this design, but a very, very close approximation to this. And they have it in a warehouse, and they're like just doing conceptual design work with this and refining kind of the concept as they go. Really phenomenal. I'm really excited. I mean, we're still a ways away from like building the like I-95 bridge this way, right? But you can start to imagine a future where this could start to be much more mainstream. And so I think that's really exciting. We can extrude plastic, we can extrude metal, we can also extrude concrete. Think about this like, you know, you put icing in a big cake decorating bag and you kind of squirt it on the cake. Well, we can do the same thing. We fill the bag with concrete or a mortar slurry, and we can extrude it out. And here is a printer that's doing just that. You can kind of see this layer by layer process, and this turns into this, right? This is a crazy guy in Minnesota. He was a contractor, a concrete contractor. He got really excited about 3D printing. He made one of these in his backyard. His neighbors thought he was nuts. Here he is printing a castle, but super exciting, right? Geometries become almost limitless. I mean, nobody can make this kind of stuff anymore, right? This is like skilled masons would be doing this work. It'd be really, really hard to cast. But if you have a 3D printer do it, it can do it from the ground up. And so here you go. Now you can start to imagine a world where this happens. And a lot of people have since done that. So you start to see things like this, right? This, in less than 24 hours, turns into this, right? So you start to see, you know, this is, I think, Russia. China was doing this. This just happened in Paris as part of a like installation for new technologies. But we can print houses, again, less than 24 hours, concrete house. And you can start to see like we have hollow structures, right? So we have really good insulation properties here. We're trapping air, which is insulating things, which is great. You know, and you just have that gantry in the middle, and it can create this geometry as you go. The only issue is here we're really thinking more like mass masonry construction. You're laying these like layers of concrete on top of one another as you go. You have really poor binding conditions between those two layers. So it's not going to be like, you know, really robust concrete, but if you make this thing big enough, it's just like laying stones on top of one another in your backyard, right? So you get a pretty good structure from that direction. So anyway, that's kind of cool and exciting from the additive side. All right, now we're flipping gears. So we did that like SLA stuff, we did the material extrusion. Now we're talking about powder bed fusion. Gosh, there's so many different acronyms these in additive. I get tired of them all the time. I have to add a new one here. Laser powder bed fusion, LPBF, whatever. That's the newest one that we're talking about this with, but it's gone through a lot of different iterations. Here, you know, again, this is going back. It was developed in the 80s at UT Austin, patent filed in 86, commercialized in 89, bought by 3D Systems in 2001. The process, this is going to look very similar. We start with a volume of powder, right? And so this can happen with both plastics, polymers, and that's where it started, but where it's moved to is metals. We have on the left here, you kind of see this is like there's two sides of the screen. These are in opposition. So as one goes up, the other one goes down. The volume on the left is your feedstock. The part on your right is your build area. and you push a thin layer of powder over the top. It's super smooth, like a sheet of paper. We fire a laser, we melt together that powder. It forms, it obviously bonds to itself, and we create a part. So we start to do this layer by layer. Lo and behold, we get really, really complex geometries with actual polymers. So unlike SLA, which has this lovely laser-based thing, that's using resins. Resins are approximating material properties. They're not as good as the traditional polymers. Here, we're actually using the traditional polymers or metals. Really expensive technology, even still to this day. My favorite example, anybody is an aviation buff, this is an F-22 Raptor. This is a US Air Force plane. When they were designing the plane, it was the same time this technology was being developed. This is a stealth fighter. And for it to be stealth, everything about it, like not only the skin of the plane has to like absorb and reflect radar, but also it can't have exhaust because the exhaust shows up in radar. And so what they want to do is they want to fully burn the fuel. So the engineers are like, all right, we need a perfect fuel to air mix. We have to like move the air at a certain rate in a like vortex. They designed this really complex, they modeled this really complex like helix within a helix that moves this air in this certain way. All their theory works out, and they took it to the manufacturing floor, and they're like, there's no way to make this, right? We'd have to machine this in tiny little layers and then weld it together. Like this is impossible to make. Well, again, this is the same time that this polymer 3D printing SLS technology was being developed. They brought in UT Austin, Carl Deckard, and 3D Systems, which had just bought them. They printed an air intake that did this thing in polymer, mounted it to the test engine, worked flawlessly, and now every F-22 Raptor that's flying today is flying with 2 3D printed air intake manifolds, right? So, I mean, like, talk about something that's in really intense conditions. This is in the start of a turbine engine sucking in air at incredible rates of speed, right? And it's still, that was the manufacturing solution. Again, we can do it with metals. The process looks the same. The laser's a little bit different. Anything from tool steel to titanium. We're doing a lot of research with this, with new materials at Lehigh with our printer. But here you go. This idea of topology optimization again. Airbus A380, we're talking about the nacelle hinge. So the nacelle is the cover that goes over the turbine engine. Relatively non-flight critical part. I mean, obviously you don't want the nacelle to fall off mid-flight because that would probably damage some houses below it or hurt some people. But like ultimately, this doesn't affect the flight hardware. So Airbus said, hey, let's look for a way that we can use additive. Let's find a case study. And so they use this as the case study. There's like 10 of these hinges on every nacelle. There's like 8 nacelles on the aircraft. The part in the back that's kind of fuzzy, that was the original part. Very simple geometry, made out of aluminum, milled out of aluminum. The part in the front, they took that same design, applied the like loading conditions to it, determined, hey, all this material isn't doing anything. This is the only material that's doing anything in this case. And so this is how you topology optimize. So they remove the material they don't want, and they 3D print it in titanium. Titanium has an incredible strength to weight ratio, so very lightweight, very high strength material. And it turns out that when you do that, the part in front ends up being 80% lighter than the part in the back. So if that thing originally weighed 10 pounds, it now weighs 2 pounds. That's crazy, right? Now, it turns out that if you 3D print things versus traditional manufacturing, it's a lot more expensive, like to the tune of like 10 times. So this part in the back, maybe it's $40. The part in the front, probably $400 if we're printing them at scale. How do you make sense of that economic model? And the answer is pretty simple. When you start to think about the fuel savings of the aircraft that's flying with this hinge, right? So it turns out that if you take this hinge, you apply it across the spectrum to all of the hinge locations on the Airbus A380, you save, whatever number of pounds of weight, and you figure out the fuel that it takes to move that around the world for a year for the typical flight time of an aircraft. And you now save, over the course of a single year, $1 million in aircraft fuel. So now Airbus can charge American Airlines $1 million more for the aircraft and say, hey, your ROI for that $1 million is 1 year in the weight savings that you're going to get from that part alone. So really phenomenal. We're also using this in medical industry. So this is a hip cup. the important thing here is actually this lattice on the back side. If you look at this, like you can see there's some small holes, there's some big holes. That's actually permeates through. It's a three-dimensional lattice. Again, impossible to make any other way aside from 3D printing. Here, this was solving the problem of if you have a grandmother or something that had an hip implant, 20 years ago, it was really bad because they were notorious for being something you had to have multiple hip surgeries for. And the answer wasn't because the hip implant itself was breaking, it was because it was becoming dislodged from the bone, right? And the reason it was becoming dislodged from the bone is all of the hip implants were smooth surface, made out of titanium, and there would be no interface between the bone and that thing. They were using cement and screws to hold it into the hip bone. Well, if you trip, most of these were being put into people who were older, who had osteoporosis or low bone density. If you trip and you have low bone density and you have screws holding this thing in, well, the screws are going to rip right out, and then you have to have another hip implant. So this was solved by the medical industry with this 3D lattice. What you see with this 3D lattice is the body doesn't see this as titanium, it actually sees it as bone. And it goes, oh, hey, bone, I'm going to grow into you. And they actually fuse together. And so after about 6 months post-surgery, the implant and the body become one. And it's reduced recurring surgeries by like 70%. It's insane. So almost every medical industry that's making implants is now moving to 3D printing for those implants. And we're starting to see it happen. We're doing a project at Lehigh with like a thumb joint. You're starting to see it with knee joints, just because it's allowing this like ingrowth, this bone ingrowth happening. So totally phenomenal. All right, completely different technology, binder jetting. This was, when I said 3D printing, this was Z Corp. They actually started this thing called 3DP, 3D printing. They took an old Hewlett Packard 2D printer that was like, printed your homework, whatever you're printing. It was broken. A bunch of students at MIT took it apart. They said, hey, what can we do with this? They drained the ink out. They put in a glue in the print head and started printing glue. And then they started gluing together flour and started to make 3D flour parts, like baking flour. And so that gave the rise to this whole concept. They filed a patent. Now it's used in a bunch of different ways. Similar process. We have build material. We have the build area. Now we have some sort of adhesive that's being pumped into a print head. Even today, we're still using HP inkjet cartridges for this. And it's being deposited on the surface because that surface looks very much like a piece of paper. That build tray drops down, another layer of material goes on top, it gets glued to itself, and the layer below, we have a 3D part. Totally phenomenal, really fast. And because it was originally inkjet printing, we can now add color to that binder and we can get full color parts, right? So you can start to see oh yeah, we can show the inner workings of different stuff. If I want to communicate things to people, I can say the camshaft. Somebody's like, what's the camshaft? You say, oh, the yellow part. Oh, okay, I understand what the camshaft is, right? So it allows you to have good visuals for doing things. Medical is using this for doing pre-surgical planning. So instead of having to look at layer after layer after layer of an MRI, they can actually 3D print out the part, find the defect, figure out how to do their surgery. This happens to be like a 6-month-old girl who had a heart defect. The surgeon said something on the MRI doesn't look right. They had just gotten a printer. He printed out this girl's heart, which is what we're looking at. And he found 2 other holes in the heart that had he gone in to repair what he thought was this one defect in the heart, not knowing that those other things were there, the girl probably would have died on the operating table. So just doing this allowed him to visualize the surgery, and he ended up saving this girl's life. So totally impactful from that range. All right. X1 took the same idea and applied it to both sand and metal. So metal, you can take metal powder, you glue it together, you put it in a sintering furnace that then heats that metal powder together and makes those metal spheres that are kind of glued together warm up enough that they touch and merge together and make a metal part. That's pretty cool. Very fast way of making metal. It's not as strong as laser sintering, but it's faster, it's cheaper. But the thing that you guys maybe are more interested in or should be more interested in is what they've been able to do with sand. And so they're gluing together sand to make sand casting molds. Here's an incredibly complex mold. And because they don't have to get like a positive out as they're printing, they just have to have drain holes for the liquid sand to come out. They can make incredibly complex geometry and then glue together these parts. And then you can see these little white holes at the top. They just pour molten metal in there, and then you have this amazing, you just break apart the sand and you have this amazing part. The reason I say that you should care about this is, Professor Nato can talk about this. Some of his research is taking the same technology, and instead of printing sand or metal powder, can we just print concrete, right? And so early stage research into printing concrete powders. And here it is, a picture of that. But the idea is that X1 actually has these huge machines, right? We can scale this up to, this thing is the size of a room. The print tray for these things is the size of a room with their Excelsior platform. And you can start to think about making structural columns, right? So I can make these like beams that are topology optimized, that are lighter weight, that are far more interesting to look at than just a solid beam, but I can do that with that process. So super exciting way of doing that. Kind of the newest thing on the scene is, I think of it as a kind of like merging of these two different technologies, this binder jetting where we're gluing stuff together, and this like laser powder bed fusion idea. And it's something that Hewlett Packard came up with. Well, they didn't come up with it. They bought the technology from a guy in England who was working at a university who designed it, but I'm not supposed to know that. Again, SLS process, which is take the laser, heat up plastic, and like make plastic parts that way, is great, but it's very slow. In the same way that SLA was slow and Carbon sort of figured out a way to deal with that. HP, the issue with that is the slowness is the laser. For each pass, the laser has to follow this thing. It can only move so quickly. HP said, great, how can we use our technology to change this? They print with HP inkjet technology a material that absorbs heat energy, and anywhere that's printed on the polymer surface absorbs enough energy to get that polymer to fuse together. Anywhere where it isn't, doesn't fuse. And so what they can do is they print, which they can do very, very quickly, and then they come by with an infrared heat source, and that goes over the whole bed at one time. And the speeds with which they're able to do this is absolutely like astounding. So these numbers at the bottom here, this 1,000, 83, 38.3, they had this part that was like a gear, and they said, all right, how fast can we print these? 83 is if we took that and we used an FDM printer. So it would take us 83 hours to print 1,000 parts with an FDM. The 38 is SLS, so that's the laser-based polymer, like laser powder-based polymer solution. It would take 38 hours to make those same 1,000 parts. With HP technology, it takes us 3. So incredibly fast process. That's just a process diagram. This is what the machine looks like. This is, they 3D printed this chain ring, and here's that chain ring. Again, it's a nylon powder that they printed with their technology, and that same chain ring is up here, and you can see it holding up a Toyota Camry. So you get a sense of how actually strong this technology is on top of everything else. And they've now started to do this full color. So I actually wish I took a picture. I have them in my office. I don't have them here. I have this flower that has this really delicate petal that's like beautifully sculpted. You would think it was real. It's not. It's 3D printed using this technology. It is phenomenal and super exciting and super fast. It's scalable to the point where we could potentially replace injection molding in the next 10 to 20 years with this. And so this is a graph we use a lot to talk about the advantages of 3D printing. Generally, the number of parts that you're trying to make, your cost per part is very high with the lower number of parts. With traditional manufacturing, it's because you have to set up your tooling, your molds, your jigs, your fixtures, all of that stuff. That's incredibly costly. Like injection molding, you could spend $500,000 on injection mold tooling for a single part. So if you're making one part, that one part costs $500,000. Now, if you're making 100 parts, you take that initial investment, you divide it by that. The plastic is essentially free. It's so cheap. And that starts to go down. So that's this like gray background box. As you make more parts with conventional manufacturing, this starts to get cheaper and cheaper and cheaper. 3D printing comes on the comes in on the scene, it's more expensive per part, but you don't have any of that initial investment. So traditional 3D printing kind of like exists in this zone. So it's cheaper, if I'm making 1,000 parts, which is kind of like where this is right now. This line is about 1,000 parts. If I'm making 1,000 parts, it's cheaper to 3D print them than it is to do traditional manufacturing. If I'm making 1,500 parts, well, I should actually go through the conventional manufacturing. What HP does to this is it moves that out to about 100,000 parts. So now if I'm making 100,000 parts or less, it's going to be cheaper to 3D print them with HP's technology. So it's exciting. It's changing the world of manufacturing in general. Material jetting, here now we have, again, similar to like inkjet cartridges, we have these little piezoelectric pumps that are pumping out tiny little droplets of material. We have a liquid resin, just like we do with SLA. We have a UV light. So the liquid resin gets dropleted out, a UV light comes over, cures it, flash cures it. Now we don't have a vat of resin anymore. We can print right on a build platform. We have one of these at Lehigh in the form of a polyjet machine. Here's tooling being made. So you can make like investment tooling with this that is pretty robust. You can also, again, they're moving to full color this technology. They're mixing materials, they're getting different material properties, they're getting different colors. Medical industry is using this a lot for training to do like mock surgeries for med students, because they're able to actually make different textures and different colors. So it looks very like lifelike organs, and students can practice doing surgeries on lifelike organs, but see what they're doing. You can also do this with metal. This is new stuff. They're doing these nano droplets of metal, curing it and then sintering it to make metal parts, but it allows you to make this whole little engine thing is only about like 2 inches tall, really, really high resolution printing with this. This is kind of an oddball, but I throw it in there just to kind of show you, this is actually one of the seven families of additive. It's sheet lamination. You can do this with literally paper, which is the first thing I'm going to show you. You can also do it with ultrasonic UAM, ultrasonic additive, where you're doing that with metal sheets. But essentially you take paper, you apply glue to a sheet of paper, you put it on top of a stack of paper. You can print on that paper color to get like ink on it to give it color. And then you come back with a knife and you cut out the profile of the 3D geometry that you want. And you do that layer by layer. The beautiful thing about this is paper is pretty cheap in the grand scheme of material. You can get like a very large model for very little cost, because I'm just going to Staples to get my material. You get, and really, really high color, but kind of weird. So this is not an orange. And if you look, you can kind of see each successive layer of paper being glued onto itself as it goes, but it looks like you'd swear you'd have an orange, right? So really, but the whole thing is solid inside, right? It's solid paper. So it doesn't give you any of that like light weighting ability. It's really more of a like visualization tool, but it's really good visualization tool. So, in archaeology, they're doing this for like reconstruction methods, things you want to put in a museum that looks good, like an original artifact, but isn't actually an original artifact. You can do that with this technology. So again, this is all 3D printed based on a 3D color scan of the actual part. You can do this with metal by taking little thin metal sheets and ultrasonically welding them down to a metal sheet below, and then coming back with a CNC mill at each layer and kind of cleaning up your profile and internal geometry. And NASA actually uses this a lot for satellite technology, because it's like really the part strength of these is incredibly good. It's almost like a wrought material. So their layer strength is really strong because it's a welding process, and they can make really, really lightweight, very complex parts with this process because they can make them hollow. Last of the seven, we're getting close, everybody hang in there. Direct energy deposition. So this is also known as lens or laser engineered net shaping. Here we fire a laser and we blow powder into it. So here's the laser coming down through a thing. There's a nozzle. There's powder coming in with these little pipes and being blown into the beam. When the metal powder hits the beam, it melts and then fuses to the surface that it's being blown into. 10 years ago, I would have said this is a dead technology. We shouldn't talk about it. But some smart people within additive Here it is. Here's an example of it actually being used. But some smart people said, well, yeah, and why I would say it was dead is it's near net shape, so it's not giving you great parts. It's very slow. So you have to do some post-processing to it, and then it takes time. But again, smart people look at stuff and see it in a different way. And they said, oh, what if we combine this with traditional manufacturing? And so there's a couple companies doing this now. They've taken a cladding head, and it just gets added to a tool changer for a traditional mill. This comes into the tool head, the powder feeder is attached to it, it fires the laser, and now you can take a part in the mill that you've machined, you can add structures to it or repair it potentially, which is a lot of what this is being used for. And then you come back in that same process in the same mill and mill it back down to spec. And so it's kind of opened up the possibility for doing lots of new cool stuff and leveraging what traditional manufacturing can do with the kind of the benefits of additive. So totally cool. So here it is, like we start with a pipe. Now we can come in, we can add these little funny like nodules to a pipe where we can make different like hoses connect to it, right? Be very, very difficult to do from scratch. I'd have to weld these little pipe nibs on, but I can have the computer do it and I can machine it as we go. So very, very cool possibility. So that's the overall spectrum of additive. I just want to cover some really cool, innovative applications because I think it's a good thing to talk about. So in the medical world, reimagining what we can do. You break your arm. What's the problem when you break your arm? Well, this is what I talk about, mass customization, right? Casts are the perfect understanding of mass customization. Everybody's arm is different. So how do we get around that as a doctor? Well, you put plaster on the arm, the plaster hardens, and now I have a perfect mold of my arm, and it holds my arm in that position while the bone heals. The problem with this is, anybody ever had a cast? Can you shower with the cast on? No. So if it's like your arm, you got to like put your arm in a plastic bag in the shower and you can't get it wet. It's always going to be itchy. So you got to like figure out all sorts of cool devices to get down in there and scratch your skin. Your skin starts to slough off because it's dying because it doesn't have air getting to it. And so there's people that are actually looking at, can we 3D scan the arm? Can we 3D print a clamshell mold, put it over the arm? And now it does all of that same structural stuff with holding it in the right position, but I have air, it's plastic, I can take a shower. There's some companies that are actually embedding electronics in there that flex your muscles, so you don't like lose muscle tissue over time. So that's kind of stuff, cool stuff. We can print collagen and grow cells on it and form like human body parts. So this is not the future. This is now. People are growing ears to replace like people who were born with deformities or lose an ear from an accident. Fairly possible to do that. The bottom right here, this is a company called Organovo. This is one of their cell printers. They are printing human livers, legit human livers to the like we're 2 years away from them being implanted in humans. They're already being used for drug trials. It's really hard to get healthy livers for drug trials. So they're 3D printing livers and using those for drug trials. The future is here, ladies and gentlemen. We are all going to be like weird 3D printed hybrids in a few years. But yeah, it's crazy. So they've solved the liver. They're working on kidneys now. You're not going to have somebody share a kidney with you. You can print your own from your own cells. It's going to be crazy town. In the world of aviation, GE Aviation, actually one of the oldest examples, their LEAP engine fuel nozzle here. It was originally like 27 separate parts. It's now one continuous 3D print. It's again 25% lighter than the original, which saves weight, which saves fuel, and it's actually 5 times more robust because it's one single print. So fascinating application. They're starting to print turbine blades, which I thought we were a long way away from, but they're able to do that. Single crystal turbine blades, totally fascinating. I mentioned Airbus had that really exciting result with their nacelle hinge. Well, they started to look at like, well, what if we just 3D print the aircraft? So clearly we're not there yet to that scale, but this is kind of what they're envisioning. They've gotten to the point where they've done the mathematical computation. They start to form this like structural lattice that forms the body of the plane. Most planes now, they're like tubes, and they're tubes on purpose. And the aluminum skin actually gives the plane the structure. Here, you don't need the aluminum skin anymore. And so the cool, fascinating thing about this is now you can like put like open panels in here, and you can like sit in the plane and have this lovely vista as you're flying. They've done some like trials with people, and they've gone like, no way in hell I'm riding in that thing. So it's still got a little ways away, but it enables them to make the whole aircraft lighter, which is going to, like, again, from an environmental perspective, it saves fuel, less CO2 emissions, all sorts of stuff, but it saves fuel as well. So really cool kind of conceptual stuff. NASA's using this thing. They have printers in space already on the space station. They're heavily invested in 3D printing technology because, you know, it takes 9 months to get to Mars, right? You start on your journey to Mars, something breaks, what are you going to do? You have to be able to like repair things in situ. You have a base on Mars, it takes a long time to get replacement parts. So they're really thinking about, you know, how do we do that? So they're really investigating 3D printing. This is literally a filament printer, a modified filament printer that they're using in space to print parts, and they've made wrenches for that. I think this actually has some, like, if you start to think long term, you start to see how this can be applied to like things like civil engineering and structures. But I love this guy. He's an artist. His name's Marcus Kaiser. And he was like super excited about 3D printing as an artist, but then got really disappointed because the cost of materials was so expensive. So being the really smart person that he was, he said, well, you know, like, where can I go on the planet where I have a whole lot of free material that's all consistently the same? And so he arrived at like, oh, I can go to the desert and I have like kind of like unlimited quantities of sand. What can I do with that sand? Well, if I apply enough energy to that sand, I can turn it into glass. And so here he is, he developed this 3D printer that he goes out there, it's got a lens that focuses the sun's light, which you have a lot of in the desert as well, right? So this is like all about in situ application. Got a lens that focuses the sun's light down on the surface. He comes out there with a 5-gallon bucket, dumps sand, smooths it out by hand with a little, you can see him there with his little like 2x4, makes it nice and smooth. And then he runs a computer, which is run by the solar panels, and it traces, it moves the lens. And here he is, you can kind of see it's a glass bowl being printed in the desert for like $0 with zero energy, because he's just using available sun's energy. And so NASA really has taken like a page out of his book, and they're thinking like, oh, when we get to Mars or we're on the moon, you know, how can we take advantage of this kind of concept of in situ manufacturing and using existing technology to do that? So they're thinking like, can we scoop up the soil, do something with it, and then actually make the habitats that the astronauts would live in? So this, again, there's like a whole division at NASA that's kind of dedicated to this right now. Totally fascinating. And I will leave you with this, my little like tearjerker story. Because this is actually the thing that I think that's so powerful about 3D printing. This is Emma Lavelle. She was born with a degenerative disease that affected her musculature and skeletal system. So she was never able to walk or even hug her parents. And so, you know, like, obviously when you have something like this, you go to the doctors a lot, and the doctors told her parents like, hey, you know, the good news is that otherwise your child is healthy. She just will need to be wheelchair bound, and you'll need to feed her and all of these things. But when she stops growing, we can think about like fitting her with an exoskeleton, and that exoskeleton can like help her move. And her dad was like, well, you know, like, why can't we do that now? Well, exoskeletons cost millions of dollars. They're incredibly complicated. They have all these like different things. And so, you know, being the engineer that he was, he sort of sat down, looked at exoskeletons and said like, my daughter weighs like 22 pounds. You know, I don't need some like giant servo motor to do this. She has some muscle, but she doesn't have enough to actually move things. So he developed this system, and you can kind of see it's cobbled together. But the key of this is there's these 3D printed components and these like industrial scale rubber bands. And so he worked with Stratasys actually, and they printed these out for him. And this is Emma taking her first steps and hugging her mom for the first time in her life. Not because some medical company like developed the exoskeleton for her, but because her dad saw the power of 3D printing, saw a problem he could solve for his daughter and make a real impact, right? And that's the thing I like the most about this technology, is it puts the power to make real change in our hands, because it makes things cheaper, it makes things faster, it gives us the tools without being experts in manufacturing to make things. And so that is the end.